Hello and welcome back to math class in session. Applications of this dot product and cross product. They have many applications in geometry, physics. Mostly they lead to a subject called linear algebra, but for now let's focus on applications of this dot product and cross product. Work, by definition, the word work, by definition, is the product of the distance an object has been displaced by the component of the force acting in the direction of that displacement. And since force is measured in newtons and displacement is in meters, the unit of work is Newton meters. These are called joules. So a 1 Newton force that pushes an object 1 meter has done 1 joule of work. In the following diagram, a force A drags an object from O along the blue vector through the length of this vector B. The component of force acting along the line of the displacement, the component of the force, so something is pulling in this direction, but it has a component of force in this direction. And that component of force is the projection of A onto B. And I've outlined it here in a blue vector. ON. And we know what that is because this is the hypotenuse of a right-angled triangle, and this is adjacent to the angle theta. And so therefore, this distance ON is magnitude of A cos theta. So ON is magnitude of A cos theta, while the work is the distance that the object was displaced, which would be the magnitude of B, multiplied by the component of force in that direction, and that component of force is ON. And so if we combine these two statements, we can see that ON is magnitude of A cos theta. Let's just sub that into the W expression. And I just turn magnitude of A and magnitude of B around. And we recognize something here. Length times cos is work done. But that's a cross product. I'm sorry, that's a dot product, isn't it? The work is a dot product. Example, snow is shoveled off of a driveway by exerting an average force on a snow shovel of 150 newtons at an angle of 30 degrees to the horizontal along this vector. Someone's pushing on a snow shovel, which is contacting the ground here and pushing snow in this direction for a total of 700 meters. And the angle that the snow shovel makes with the horizontal is 30 degrees. So if this is the snow shovel and this is the horizontal, this would be the 30 degrees. Calculate the work done if the total displacement that the shovel is pushed is 700 meters. So we have to calculate the work. So we need the dot product between these two vectors. Solution, we note that the angle between, and I've underlined the word between, the force and the direction of displacement is 30 degrees. But it kind of looks from the diagram like it might be 150 degrees because I can see 150 degrees here, the supplement of 30, that exists between the 700 meters and the force pushing down at 150 meters, newtons, excuse me. So the thing is this. By definition, the word between, when it talks about vectors, is between vectors when they are arranged tail to tail. These two vectors are arranged head to tail. And so what we need to do is just redraw one of these vectors up here, for example. There's our 700 meters up there, and we can see a Z pattern which puts 30 degrees when they are arranged tail to tail. And so now I know that the work done is going to be length times cos of the angle between them, which is 30 degrees. It's that simple. Here's a proof. It's a proof of the fact that the magnitude of a cross product is length times sine of theta. The cross product, by definition, is this formula. And if we square both sides, well, what have we done here? We've taken the magnitude squared. Now we know that the magnitude is the sum of the squares of the components with a square root sign, but I squared that, so the square of the magnitude is the sum of the squares of the components. Now, if you multiply them, if you square each of these binomials and sort out and count up the terms, these are the terms you get. Square this first binomial, we're going to get a square, we're going to get another square, and 2 times the product of the two terms. So it's squaring a binomial. And we did it again, and we did it again. Now I'm going to make a claim. I can regroup all of these terms into something that looks like this. And you might say, how did you do that? And my answer is, it might take an afternoon of tinkering and regrouping and thinking about it, but you can confirm that it's true, because if you were to multiply this out and square this out and subtract these terms and then compare it to this, you'll see that it's true. So I can use it in a proof by saying these terms can be regrouped like that, and leave it to you to confirm that yes, that's true. If I square that out and multiply that out and collect like terms, this is what I get. Carrying that forward, well, what have we got here? The square of the magnitude of A will be A1 squared plus A2 squared plus A3 squared. So this is the square of the magnitude of A, just as this is the square of the magnitude of B, and this is the square of this expression, which is the dot product of A and B. A1B1 plus A2B2 plus A3B3. By definition, that's a dot product, and it's squared. And we know that the dot product is length times cos. So each of them are squared because it's the dot product squared. And we can factor out this magnitude of A squared times the magnitude of B squared. Common factor. We get 1 minus cos squared. And from identities, that tells us that's sine squared, because 1 minus cos squared is sine squared. And now take square root both sides, and we have the magnitude of the cross product is length times sine. This is going to come in very handy. Consider the vectors A and B and the parallelogram formed by them. So here's A, here's B, with an angle between them. Notice they're arranged tail to tail. The angle between them is cos theta, and they form a parallelogram. The area of that parallelogram is base times height, kind of like a rectangle. Magnitude of the base times height. Now, the height, we know, is, consider this magnitude here. This is a hypotenuse multiplied by a sine, because this is opposite the hypotenuse. So magnitude of A times the sine of theta will be our height. And so we'll take this magnitude of A times sine theta and plug it right in there for H. And so the parallelogram, the area of it, you could rearrange this. The order of placing them doesn't matter. But The area of the parallelogram is length times sine. Now we've just seen that recently. Length times sine. That's the magnitude of the cross product. Just let me back up here for a second. The magnitude of the cross product was length times sine. The area of a parallelogram is length times sine. And so the area of a parallelogram is the magnitude of the cross product. And that's going to come in handy, particularly if we wanted to find the area of a triangle, which is exactly half of this parallelogram. Example, determine the area of the triangle formed in 3 space, by 3 points in 3 space. So you can start to think celestially here, and we've got these 3 points hovering in the air somewhere with these coordinates, and they form a triangle when you join them. But it's in 3 space, so very difficult to draw, but we can still get the area of the triangle formed by those 3 points because we know that. We'll find the position vectors of any 2 sides of the triangle, say PQ and PR, and then we've got a couple of vectors. And take half of the area of the parallelogram formed by them. So our plan is to find a couple of vectors that form this parallelogram and then take half of it, because if I were to draw across here, that would be half of the parallelogram. So we'll find, say, PQ, which we know how to do very easily, subtracting backwards. -2 subtract 5, 10 subtract -4, -6 subtract 8. And PR, again, 8 subtract 5, 2 subtract -4, -4 subtract 8. And we've got our 2 vectors, and we know that the area of that triangle will be half of the magnitude of the cross. So let's find the cross product. Now, I just went ahead and did it. I suggest that you pause the video and do this yourself. When you cross these 2, this is the cross product, and it's the square of the cross is the square of, well, -84 squared plus, it's the sum of the 3 components squared. And so the actual magnitude of the cross is the square root of that. And so the area of the triangle formed by our 3 points in celestial 3 space is, ta-da, half of that. And so like magic, we can conceive of points in 3 space that form a triangle, and we can get the area of that triangle. Moving on, torque. Torque is a twisting force. The magnitude of the, well, let's take a look at this. If this was a wrench, R for radius, but let's say this was a wrench and this was a nut on a bolt, and we were trying to loosen it or tighten it. So this is a wrench, and this force is us, or a person, pulling on this wrench to try to twist. So the twisting force takes place at M. So torque is a twisting force. And the magnitude of the torque is the product of the magnitude of the force that you exert times the distance d that force is away from the point where the torque is being exerted. Now, it's not the length of the wrench. It's this straight over distance, the distance from the point of torque to where the force is. So the right angle distance. But this does explain why a longer wrench gives us more leverage over the torque, because a longer wrench, when we get the product, we're multiplying the force by a larger distance, because the wrench creates a longer wrench creates a longer distance. So the torque is force times distance. That's what this paragraph says. The magnitude of the torque is the product of the magnitude of the exerted force and the distance d from the point of rotation to the line of the exerted force, this distance d. And this torque is measured in Newton meters or joules, because it is, after all, newtons times meters, because it's force times distance. And we can see from our diagram here that the distance is the magnitude of this radius, which would be the length of the wrench, multiplied by the sine of theta. So plugging this into our formula for torque, we get torque is actually magnitude of the force times the magnitude of that radius multiplied by the sine of that theta. Here we have length times sine between two vectors. How about that? We've seen that before. That's the magnitude of the cross product. Okay. The magnitude of the torque is the magnitude of the cross product. Hang on. Moving on, example, a 12-year-old girl, well, it doesn't matter about the age, it's just a distraction. It doesn't matter if it's a girl, it could be a 85-year-old man who weighs 100 pounds, is out for a bike ride. Calculate the torque she applies to the sprocket of her bike when the pedal arm makes an angle of 45 degrees with the vertical if the distance from the sprocket to the middle of the pedal is 15 centimeters. First of all, we need to understand that when this person pushes down on the pedal, the 100 pounds of weight is the force pointing straight down. But we have to turn pounds into newtons. So first we need to turn pounds into kilograms. We'll take 100 pounds and divide by 2.205 because that's how many pounds there is in a kilogram. So we know that this person weighs 45.35 kilograms, and we'll multiply that by 9.8 to turn it into newtons. So we know the force involved is 444.4 newtons. Time for a diagram. So here's the pedal. There's the force of 444.4 newtons. And the length of this, well, it was the wrench in the other diagram, but the length of this radius is 15 centimeters. Let's convert it to meters. And the angle that between these is 45 degrees. And so, therefore, we'll go length times sine. And that's how many joules of torque is being applied at the sprocket. 47.1 joules. Summary. Work is force times distance, which is the dot product. Magnitude of the cross is length times sine of the angle between them. The magnitude of the cross product is also the area of the parallelogram formed by the two vectors A and B. And the magnitude of the cross product is also the magnitude of the torque applied in our diagram. Just some of the applications of dot products and cross products to physical sciences.